And so the main object for the talk will be Poisson-Lie groups. And so in the first lecture, we don't have anything. Our course is called quantum groups. We don't have any quantum groups on the first lecture. And I should say today will not have any quantum groups. But so the main message of the first lecture is that if we want to quantize something, we need to have something Poisson. And if we want to quantize group, some Lie group, then we should have some Poisson structure in this Lie group. And it is natural to ask that this Poisson structure will be in some sense related to the Lie group structure. So this is the notion of Poisson-Lie group. Okay. So definition. G is a Poisson. Okay, simply okay. If G is Lie group, if G is Poisson, and the multiplication is Poisson map. So if first two conditions are quite obvious. G is a Lie group. G is Poisson manifold. And third condition is the following: the product map G times G to G is Poisson map. What does this mean, Poisson map? It means that if we have any functions so the last condition means the following: if we have any two functions, let me write in phi and psi functions on G, then we can compute their bracket phi and psi, and then substitute some product of 2 points G H. And we can do actually this in two ways. So one way we can compute the bracket as written. Another way we can take this function and then take the inverse image on G times G, and then compute the bracket on this product G times G. So product of two, here G is a Poisson manifold, so product of two Poisson manifolds is again Poisson manifold. We can just take the sum of pi1 and pi2, sum of Poisson bivectors. So in terms of the equation, this will be the following equation. So it will be equal to bracket phi psi of GH for H fixed. So we fix H and consider this function phi of GH and psi of GH as a function just on G. And plus this the similar term, bracket F phi and psi of GH for G fixed. This another way to state the third condition. Okay.
It is in some sense Leibniz rule.
No, I wouldn't say so. I don't know. This is what it is. The competitive fact that the product is Poisson map.
So it can be treated as definition of the Poisson map, yes? from G times
This,
G to G. That it satisfies the following
yes.
property.
This is the definition of the Poisson map in this case.
Okay.
Let me give a remark.
Sorry, may I try to say it differently? It looks like we are just taking a sum of two Poisson tensors on the first manifold and on the second manifold. So
Yes.
P equals P1 plus P2.
Yes, so on G1 times G time we have P1 plus P2 Poisson manifold, and G we have Poisson tensor pi. Yes. Exactly. This is the difference. So okay. Okay, I plan to give a remark. Okay, maybe one color. E to G, which usually in definition of the group, we also have inversion. So for inversion, we do not impose conditions that this map is Poisson. Actually, there are two reasons. First reason, this map is not Poisson. Second reason is this map has another property. It is a, how it's called, anti-Poisson map. So bracket for any two function, phi bracket, this bracket is equal to minus bracket. This is not obvious, but this can be. It is not difficult to prove. I will not do this, but it's not. So condition is just for the multiplication. Okay, let us go to consider some examples. And we have two examples. We'll have first example will be quite trivial. Consider group G is consider dual space to the algebra G star as a group with respect to addition. It is a group, it's a Lie group. Of course, addition is smooth, everything is okay. And on the other hand, G star has the structure of the Poisson manifold, as we mentioned before. Hence, the first two conditions, Lie group and Poisson map, are satisfied. The only question is about is it Poisson map? Let's check this. How to organize the computation. So let's take okay, let me copy the formula. Okay, here phi psi are functions. For G star, everything is generated by the linear function, so I can take this just two linear functions, and G and H I can take points in G star, so two linear function G star. So phi and psi, here we have psi and psi will be Xi and eta elements of G, and G and H will be two alpha and beta elements of G star. Then our computation is a following. We need to show that cosine data for the alpha plus b is equal to what's written in the right side. In coordinates, cosine eta are linear. So, how to say it better? We can write them as a sum of, say, so psi of alpha plus b is equal to psi of alpha plus psi of beta, and similar for eta. Okay. How to say it? I'm trying to say that our bracket is linear also, so it is defined by the, if we have some structure constants, and the bracket of xi xj is sum cijk xk, and then we substitute each xi as a sum of xi prime plus xi 2 prime, and similar for xj, we substitute xj prime plus xj 2 prime, and compute bracket, and we get in any of this computation we get sum of cijk xk prime plus xk 2 prime.
What is x prime and x2 prime?
X prime and x2 prime are coordinates and for alpha and for beta, if you want. Or we have a map from, we have a summation map from G star times G star to G star. Okay, maybe I haven't prepared accurately this computation, so I will not stay for long on this point, but and I will try to make it better in the slides. We have a map from G star times G star to G star, and in coordinates this map is this is just summation. So as written here, we have coordinates on this G star are sums of the coordinates here and here. And now let's take two functions here. I to take coordinate function and psi and xj. Its bracket is given by the following formula. On the other hand, we can substitute instead of xi and xj, we can write this xi and xj as a sums. So it will be xi prime plus xi2 prime, xj prime plus xj2 prime, and then compute bracket using the right side. So we have separate bracket on prime side for prime coordinates and bracket for 2 prime coordinates. Well, this will equal to sum of cijk of xk prime plus sum of cijk xk2 prime. And these two formulas agrees. Yeah. Okay, we checked relation. Let me give. I plan to give 2 examples on the slide, but anyway.
Sorry, can I have a question?
Yes.
maybe it is obvious, but why we decided that structure constants for xi are same for as for xi prime and xi double prime?
This is a definition of the Poisson structure here.
Okay, so sorry.
Poisson structure here is defined as a product. Okay, and let me give another example. Example will be following. Let G be some matrix group, say GLN or any other matrix group is okay. Then we can define bracket by the following formula. What's written here? So L is a matrix which consists of the coordinate functions. So, for example, if our group is some GL2, then we have matrix A, B, C, D. So we have 4 functions in our group: A, B, C, and D. If our group is not GL2, it is SL2, then we have some conditions this function. But anyway, these functions generate the full algebra functions, at least algebraic functions. So L is a matrix, and here we take one matrix of coordinate functions, another matrix of coordinate functions, and compute this. I would say this is standard notation, this theory. So we have tensor product with comma. It means that now we will have matrix of the size, in this case, we have a matrix of size 4 by 4. So it will be a matrix which here we'll have bracket of A and A. Then we will have bracket of, I don't know, A and B, A and C, A and D. Here we'll have bracket of C and A, C and B, C and C, C and D. And also I don't have space, but I hope it is not necessary to write. We have 4 by 4 matrix in this case example. And on the right side, we have commutator of 2, again, 4 by 4 matrices. So here, this L1 tensor L2, it will be again 4 by 4 matrix. It acts on the tensor product. This matrix acts on some 2-dimensional space. L1 tensor L2 acts on the tensor product of 2 such 2-dimensional spaces. So it will be 4 by 4 matrix. And R will be another 4 by 4 matrix, which is given, which is some parameter. Which we need to find somewhere this R matrix in order to define this tensor, this bracket. So R is some matrix, and this is, maybe I should say, this will be some classical R matrix, whatever it means, but it's given. It is not, don't depend on L or anything else. This, I don't know, maybe question to audience whether you follow my definitions. Can you say, is it bracket constant, linear, quadratic, or something else in coordinate functions?
Well, since L1 O times L2 is a quadratic expression, it's quadratic, it has quadratic.
Yes, this is, yes. Okay, at least one person is still here. So this bracket is quadratic. but and I want to say that this for this bracket we have the we had the third property of the Poisson-Lie group. So the map from G times G to G is the Poisson map, and this is quite standard identity. So so if we take, okay, let me write computation. So okay, and that's it. So we have a map from G times G to G, and L1, L2 are matrices which consist of function first G, L1 prime, L2 prime correspond to second G. So here we compute bracket for the first. Here I compute bracket for say for the in terms of the first coordinate. Here's the bracket in terms of the second coordinates, and then we multiply here and here. So this is again the same as this formula for the Poisson. Any questions?
Yeah, you should. I don't understand why it is the same as in definition. So we have.
Because how matrix function changes if you multiply it from left or right group action? It changes as a multiplication by matrix from left or right. So you compute the bracket in the one copy of group and then multiply it by a matrix from left or right correspondingly.
So I either compute bracket for the one copy of group, either for another copy of group. This product you probably don't see here. It is it's hidden in the fact that here I compute bracket for this function, not for this function. So if you can think about H fixed, so this L1 prime and L2 prime are constant matrices, and therefore these functions are linear combinations of these functions, and the linear transformation is given by multiplication to the right by this matrix. So this, okay, my attempt to explain why this term should be compared with this term, and for this similar for the second. Makes sense? No. Okay, if somebody wants to ask, ask. I will speed up at some point, or.
Okay, I have a question. So the thing is that we impose this quadratic Poisson structure, and we have a property that we should have a Poisson-Lie group. So we should have this property, which is the second bullet on this slide, and we proved that this doesn't impose any condition on the classical R matrix. It is automatically satisfied, yes?
Third bullet is automatically satisfied. Yes.
Oh, okay, yes.
But I didn't say anything about second bullet. So actually, in order to, if you want R to define the Poisson bracket, we need to have, so the second bullet, R should satisfy something. So we want this bracket to be skew symmetric. and we want to have identity. And both these equations give us some conditions on R. Symmetricity, for example, and modified classical Young-Baxter equation. I will not say about classical Young-Baxter. I will not talk about classical Young-Baxter today, next time. But I just want to you to keep this in mind as a non-trivial example. So first example where bracket is linear can be viewed somehow. Okay, we have two examples. Two is good to start.
Okay, and may I ask another question? Where does R live? So it is a
here coordinately it leaves matrices, tensor matrices.
Okay.
But yeah, you mean that I want, if for example this L satisfies some equation, we have not just yes, better to say that it lives in G times G, of course. In order to have, I mean, if L satisfies some equation, for example, SL2, then we need, in this bracket, we need to have traceless matrices. It will lead to some equations on the derivatives. So equation actually in G times G.
Okay, thank you.
Sorry, I've got a question too. So we proved the property of Poisson map for quadratic functions of entries of L, yes, and for functions of higher degrees, we can do something like Jacobi identity and.
No, that's the linear functions on the entries of L. We prove for linear functions, so for any, so hence we prove for any function because any other function is expressed in terms of the coordinate function. Why do you mean quadratic?
Because it's L1 prime and L2 prime here.
L1 times L, yes, we take coordinate function on this matrix L1 times L1 prime, which is so it is just coordinate function. It looks quadratic because it is its argument is a product, but it is still coordinate function. Okay. It is quadratic. It is quadratic on G times G if you want, but we need to prove for any function on this G, and for this G we take coordinate function.
Mm-hmm. Okay.
No, it is. I definitely give some problem about this stuff because I don't know. For me personally, it took some time to understand this and to feel safe about this. All words are quite good. Poisson map, okay, but what does mean coordinates? You have to do some calculation. I mean, yeah, I had to do some calculation in order to understand. Okay, so we are in the middle of the talk. So, and I mean, according to time, not according to my plan, of course. And we already discussed the half of the title of the lecture. Let us discuss another half of the title. Another half was Lie bialgebras. And I should say at the beginning, Lie bialgebras is an infinitesimal structure which correspond to Poisson-Lie groups. As usual in the Lie theory, we want to come from Lie groups to Lie algebras because not to forget about calculus and just work with some algebra. Let's do it in this case. Okay, so let me I will give definition of Lie bialgebra, but I probably first I want to come to get it somehow from the definition of Poisson-Lie group. So this is my main relation for the Poisson-Lie group. In terms of the Poisson bivector pi, it means the following. So we have a Poisson bivector at the point GH, and it should equal to Poisson bivector at point G acted by here we have action of the right multiplication. So H, and here we'll have similar d lambda G applied to Poisson bivector point H. Maybe I need to write the notation. So rho H is G to G maps H point X to XH, and lambda H from G to G maps each point to HX. Okay. For example, we can put G equal H equal to E, and then we get that Poisson bivector of E is equal to Poisson bivector of E plus Poisson bivector of E. We have to study Poisson bivector in the origin, in the identity. The E in our group, the identity in our group, because we want to come to Lie algebra. And we immediately get quite clear conditions that this Poisson bivector in the E is equal to 0. So Poisson bivector itself at this point doesn't give us any information. In particular, we see that Poisson-Lie groups are not symplectic. No way. But still, we have some information. And information follows. So we can do it in the following manner. So I just copy this slide and then continue writing. So we have a map. We can take any two functions. Let me write it as an item. Take any two functions f phi psi, which are functions on our group, and assume that these functions vanish at the origin. Then the bracket also vanishes in the origin, because pi at the origin is equal to 0. And but now we look at this at the first non-trivial term. So we have we constructed a map from G star times G star to G star. Which maps differential phi times differential psi to a differential of the bracket phi and psi. It is easy to see that this map do not depend only on the differential of the phi of psi. So if we change higher terms in the expansion near the origin, we'll get the same thing. Another thing which is also easy to see, that this map is antisymmetric because the bracket was antisymmetric, and this map satisfies Jacobi identity. Hence, we define the Lie algebra structure on the G star. Is the definition clear? Can anybody ask?
Misha, I have another question to slow your lecture. The question is, what are the abstractions for a Lie group to be a PoissonLie group? So what can you give an example of a Lie group that is not a PoissonLie group?
Any Lie group is PoissonLie group with trivial bracket with 0 Poisson structure.
It's not interesting. Okay.
No, I agree with it's not interesting, but we have to ask question differently. Other questions?
Probably, can you go to the previous slide? And here you write that pi of dh is equal to d rho times d pi of d. Yes. And what do you mean by this dot, by this product?
This is not product. This is action. Maybe I cannot.
How this action is defined?
We have an action. We have a row row h which acts from G to G. Hence, it maps vector fields to vector fields. And here we have bivector, so we can map bivector to bivector.
So this is push forward.
Yes, yes, this push forward.
Push forward is usually not notated by d of map, which is one form, but the star somewhere on the top or on the bottom.
D of the map is a Jacobian.
Okay. Okay, because I understood this as one form, and I was missed for last minute.
No, this is. If you want, this is a matrix which consists of one form.
Yeah. Now I understand, but this, I thought that this is a Durham differential.
So it will be better for you if I write here star.
Yeah. Thank you. No. Yes, thank you. Now it's clear.
Sorry, what again are those objects you just rewritten?
These objects?
Yes.
We have a map from G to G, multiplication to the right, and under this map, we have vector fields are transformed by the matrix which is Jacobian on this map. Pi is a bivector field, so we take tensor product of two Jacobians and then transform by it pi. So you see, this is bivector. This is pi in point G. So this pi of G belongs to the second tensor power of the tangent space of the group in point G. And I want to come to the point GH. So hence I take this map.
Sorry, maybe I missed something, but your notation was correct. So this is indeed a differential. Yes?
Yes.
Okay.
I think everything was correct, but maybe not perfect. Definitely not perfect.
Sorry, again, one obvious question actually. On the next slide. When we write this from G star times G star to G star, we take all the differentials of these maps at unity. Yes.
Yes.
Okay.
Okay. Let me say there is another way to define this structure. Namely, one we can take. We have our tensor pi, and we can take. And using pi, we can use, say, left translation, so we can have a map from G. Okay, another way. We have a map from G to lambda to G, which goes to the following: element G goes to say LG star applied to P of G. And now we take differential at the identity of the group and get a map from G to lambda 2 of G. And this map is dual to this one. This map will be denoted by delta. Here, okay. So actually, we have two relations, two structures. First, we have structure of Lie algebra G. On Lie algebra G, we have structure of Lie algebra on its dual space. This is why it's called bialgebra. And this is not the end, because I didn't use here in the definition. I used Poisson structure. I used this Poisson structure vanishes on the origin, but actually this is not the full story. I didn't use fully the fact that we have PoissonLie group. So actually, these structures are compatible more, and I will give it in the definition.
Sorry, on previous slide at the bottom, you
Yes.
got as argument of pi. Don't you have G to minus first?
Yes, I've lost somewhere -1. For example, here.
So we move this vector, yes, from G of -1 to unity, where
Yes.
we got the algebra tangent space. Yes.
Yes.
Okay.
Okay, so Lie bialgebra. Okay, this definition. Is a following data is a Lie algebra G bracket with bracket and delta, which maps from G to lambda to G, which is can be called co-commutator or co-bracket, such that the delta star satisfy Jacobi relation. And we also have one relation which relate these two structures, namely plus delta of commutator A and B is equal to commutator delta of A and has now proposition if G is Poisson-Lie group, then G is Lie bialgebra. So this proposition means that this condition, this is called co-cycle condition for some reason, is satisfied. And it is not difficult to prove, but I will not do it because I'm moving too slowly, and I either give it as a problem or write the proof in the slides. So the proof will appear. Any questions?
It's a big question. What is delta star, which satisfies the Kobe relation?
Dual map from lambda 2 of G star to G star.
A dual, sorry.
And this
dual map. Okay.
We have delta, and this is delta star.
Okay, thank you.
Maybe I put as a remark that here definition was not symmetric. I take G, take its structure of Lie algebra, and take its coproduct delta, and I say that the G star is also Lie algebra, but it appears somehow differently. But actually, this is symmetric. So we can. I don't know. Okay, definition is actually symmetric. Or better to say, not definition, notion is symmetric. So we can write, sometimes we will write G delta, or we will write G star. You can say delta is. So this can, or we can start on the opposite, write G star G. In order to see this symmetry, we will come to one more notion. I'm sorry, lecture looks like a series of definitions, and in order to understand something, you have to work out examples, which I try to give you in problems. But anyway, let me go to the next definition. It is a Manin triple. It is another way to define this structure of Lie bialgebra, which is maybe better to understand and better to have some examples. So Manin triple, okay, let me get definition. Triple is, as you see, as you understand, triple G plus G minus, where this synthesis is as the following. So first, G is a Lie algebra with non-degenerate in symmetric form. Symmetric, invariant. G plus and G minus are Lie subalgebras. G is a G plus G minus as vector space. And maybe I put it as remark, not as Lie algebra. And the last, I don't know why I call it G plus and G minus are isotropic for our bracket. This is a definition which probably looks completely unrelated to what was before, except the notation that we have some Lie algebra, or maybe not, or maybe related. But any questions?
Isotropic, what does it mean? That this scalar product of two elements, one from G plus, another from G minus, is 0, yes? Or?
No, each of them is isotropic. So scalar product of two elements of G plus is 0. Two elements of G minus is also 0.
Okay, and to direct sum in the sense of Lie algebras, we also need that elements from one commutes with elements from another, yes?
This is not true, yes. Not as Lie algebra.
And this is not true in this case. We can see.
Yes, yes.
Okay.
Yes, yes.
And what about example? I can think about positive nilpotent Lie algebra and negative nilpotent Lie algebra, but where the Cartan goes.
So what? Yes, you're absolutely right. So nilpotent G plus and plus G minus and minus is not an example. There are similar examples. I will give examples, but before I want to stay for a moment and just in words at least say why minor triples are related to Poisson-Lie groups or Lie bialgebras. So the notion of Poisson-Lie groups is due to Drinfeld. Actually, he calls them Hamilton-Lie groups, but never mind. And Lie bialgebras are also due to Drinfeld, and he invented them. He proves theorem, which I don't have time to discuss. I put on slides that there is actually standard equivalent, standard in Lie theory equivalence between Poisson-Lie groups and Lie bialgebras. So it's okay, but Lie bialgebra is maybe not easy thing to have in mind. Some cocycle condition to structures on the space and on its dual. And what is Manin's invention here, or at least it's called Manin's triple, that the structure of Lie bialgebra can be encoded in Manin triple. And I hope, and I try to explain it in the next slide. So how to call it? Manin triple Lie bialgebras. So assume that we have Manin triple G, G minus, G plus. So the theorem set is Manin triple here. Then the theorem says that then G, any of them says G plus is Lie by algebra. But to say G plus, G minus is Lie by algebra. Oh, what do I mean here? So remember, in the definition, proof. Okay, let me be more honest. It's not proof, just comment. So remember that in the definition of the Main triple, we have product which is not degenerate, and it is it vanishes on G plus and G minus. Hence, G plus and G minus are dual with respect to this bracket, this product scalar. So G minus is dual with respect to the scalar product. So G minus we can identify with G plus star. So just from the definition of the Manin triple, we have two structures, two Lie algebra structures, one on G plus and another on the G plus star, which is identified with G minus. Okay. And where is this cocycle condition? The cocycle condition is hidden in following. So when we try to check Jacobi, if we go in the opposite direction, so assume that we have G star is on the opposite, it's Lie by algebra. Or better to use another maybe letter. Sorry, maybe I put here A. Lie by algebra. Then we can define G as a direct sum of A plus A star. And we want to define on G the structure of Lie algebra. So we know how to take the commutator of two elements of A. To also be should be some element of A. We know how to take the commutator of two elements of A star. The only thing which you have to define is a commutator of two elements of A and A star. And it is defined using the structure constants, the same structure constant which you have on A and A star. And the cocycle condition is a Jacobi identity for the elements which of mixed in mixed case where we have elements of both A and from A star. So here I just commented about errors in both directions. So if we start from the Manin triple, then how to get by algebra? We take, say, G minus, we take dual space G plus star, hence we have the algebra on G minus and on the dual space. We have G minus, we have G minus, okay, we have G plus or G plus star, we have the algebra structure on both of them, and they are compatible, and compatibility is hidden in the fact that the whole G is a Lie algebra. So we have one module, we have Jacobi relation, which takes two elements, say, from G plus and one from G minus, or an opposite. And this is a cocycle condition. And in opposite direction, we take this in the Poisson cocycle condition, we have the algebra structure. I will write proof more explicitly in slides, and this is also given in the literature. Just in order to finish more or less in time, I want to go further if there's no questions. And by going further, I mean that I finally want to consider some examples of the Lie by algebras. In a sense, I consider examples of Manin triples. And I suppose it's will be actually end of the talk. There is some story which I plan to discuss, but there's no time. I will discuss it. Hence, I have discussed it next time. But for today, we consider actually the two. We consider some examples. First example, as Vanya asked, so let's take G to be simple algebra. Then, for simple algebra, we have Cartan decomposition. Is it called Cartan or n plus h plus n plus? And of course, both n plus and n minus are isotropic, but their sum is not whole G, and we need to do something with H. And in general, this is not possible. The reason can be said quite naive. So if you have Manin triple, then our subspaces G minus G plus are necessarily Lagrangian. They are isotropic, the form is non-degenerate, so they both should have half of the dimension of the G. So G should be even dimensional. But for simple algebras, they can be even dimensional, but their dimension can be odd. For example, there is simple algebra of the dimension 3, or I don't know, 15, or many other numbers. So this doesn't work, but there is a way to treat this. Let us define, okay, let me put it here. G is equal. Let us define another Lie algebra, Q, which is direct sum G plus H. In this Lie algebra, we have two subalgebras. We have a subalgebra Q plus, which consists of elements of xy, such that x, or maybe AB, A belongs to n plus, B belongs to H, and projection of A is equal to B. And we have another subalgebra Q minus, which consists again of the pairs AB. A belongs to n minus, B belongs to H, and projection of A equal to minus B. Let me think. Yes, I think correct. Yes. Probably Pasha will ask what I mean by this projection, or is it clear?
Just it seems strange because G is sum of all of this. Yes.
Let me write here B instead of N in order to make this correct. Now it's better, or it's still strange?
But
you cannot.
Now what is B?
What is B? Okay. B is this.
Okay.
And B minus is this. And I also want to define the scalar product on this Q. Scalar product of pairs x1, y1, x2, y2 is equal to scalar product x1, x2 minus scalar product y1, y2. What's going on? How to delete this? Okay. I see. So I defined some Lie algebra Q. It's two subalgebras, and here maybe I should write Q in. And scalar product on Q. Now I'm claiming that this two, then all conditions of the Manin triple are satisfied. Let me go to this list, and in principle I can copy it. But it's not very visible, but you can see the list. First, I don't know, is it clear that everything is satisfied? Should I comment? Pasha, is it clear? Or Koля, who else can ask?
Sorry, what is this form belonging from x1, y1, x2, y2? What is it about?
It is we have it is a definition of the form on Q.
Okay.
On Q. And I'm claiming that Q plus and Q minus are Lie subalgebras, and we have decomposition of the vector space, and they are isotropic. So this is first example. Let me give a few more examples. One example is the following. So if we started from the very trivial example, G is a Lie group with, I mean, example which I gave to Misha, Lie group with trivial Poisson bracket. Then what we have? We have G star will be abelian. Then in this case, okay, I will write Q for the Manin triple. Q will be G plus G star, and the scalar product will be pairing between G and G star, and the bracket is 0. Bracket is 0 on G star, and bracket of G and G is as it should be, and bracket between G and G star I think will be coadjoint action. Or 0, let's say. Yes, I think it will be coadjoint action. Okay, let me give one more example. Again, let G be a simple Lie algebra. One can take as a Q the algebra of Laurent. This is Laurent polynomials with coefficients in G. And as a subalgebra Q plus, we take Laurent polynomials with positive powers, and as subalgebra Q minus, take Laurent polynomials with negative power. And the bracket Fg is the residue for t equals 0 of f times g. No. No, I think first option was correct. Fg. This bracket is symmetric. Each of the subalgebras Q plus and Q minus are isotropic. This is a dimensional example, but for many triples we don't have. It's not necessary to take any dual, go to any dual space, so infinite dimensional doesn't lead to any problem. And that's it. This example. This is Lisa-Balgeras, but they do not compute, obviously. I mean, saying a few words after the end of the, maybe we will not come to this example in the course, so I should say it now that this example after in the end lead to Yangians. I'm not sure that we will come to this. Okay, and maybe the last example. Which I like, and I plan to discuss it today. I didn't, but maybe I will discuss it next time. That we take as algebra Q, we take direct sum G plus G, and as an algebra Q plus, we take a set of elements A for A in G. And for algebra Q minus, we take set of elements A and B. A is in B plus, B in B minus, and projection of A plus projection of B is equal to 0. And the scalar product will be defined by the formula as we have before. Just the same. And why this example is interesting? Because in this example, we see the structure of Lie bialgebra on the simple algebra G. So G, simple algebra appears here not as a, not in the definition of the triple, not as a whole algebra G, but as one of these two pieces. So as an algebra in which we want to have Lie bialgebra structure, or as a or we will have Poisson-Lie group structure on the corresponding group. So this example, maybe I'll go once again to it, says that in this case that we have Poisson-Lie group structure on a simple Lie group. Some, I would say it was a canonical way. This is why.
But the direct sum of Q plus Q minus do not cover entire Q.
Why do you think so?
Because, for example, element AB, where A is in B minus and B is in B plus, do not belong neither to Q plus nor to Q minus.
They shouldn't belong to any of them, they should.
But it belongs to Q.
Okay, let us discuss it. Take G is equal to SL2, okay? So you want to take element of what type? F, E, yes? Коля?
Yes, yes. Mhm.
This element can be written as F plus E
Mhm.
plus minus E minus F. This belongs to Q plus. This belongs to Q minus.
But where is diagonal part? So we have also
You started from the element. We started from the element without diagonal part. If you want, I can edit what. Where
I mean that this is not equality. We have to also to subtract FF and EE.
Where you are complaining about this equality?
Yeah, I mean that there is 4 terms on the right hand side, and you written only one.
Why for this? Is
I mean,
sum, no, not product.
Ah, sorry. Yes, yes, you're right. Mhm.
Okay, I'm out of time. I don't plan to start new item. I plan to stop here. If there's no more questions, then I stop the recording and stay in this channel for some, in this meeting for some time if somebody wants to ask some private questions. Maybe I repeat, if you want to receive information about this course, please write your email to the chat.